Okay, in this example, we see that Sam has a mass of 75 kilograms and takes off across level snow on his jet-powered skis. The skis have a thrust of 200 newtons and a coefficient of kinetic friction on snow of 0.1. Unfortunately, the skis run out of fuel after only 10 seconds. So we have to find out what is Sam's top speed and how far has Sam traveled when he finally coasts to a stop. Okay, so let's start. First thing we're going to do is draw a picture. So we'll draw a picture over here. So I've got, let's say this is snow, and let's say this is one ski, another ski, and this is Sam. And he's got, let's say he's got ski poles, and he's going this way. He also has a jetpack, so we'll just make this like fiery on the end of his skis. Right, and so let's first do our boundary. So we can see that Sam, the boundary is we have, so force of gravity, we'll say it's center of his body. And is there an undo? No. All right, well, the rest of the forces I'm going to put in different colors. So this is my force of gravity. And we've got a force of the normal on the skis, so we're going to point that up, force of the normal. And then we also have the thrust force. So we're going to say the thrust force comes here. So this is going to be our force of thrust. And we do have kinetic friction. So we're going to say our kinetic friction looks like that. Force of friction. Okay, and now we can translate that to our free body diagram. So we're going to have a free body diagram. We're going to have the force of the normal. We're going to have the force of gravity. We're going to have the force of thrust this way, and we're going to have the force of friction this way. So one thing to note is that we're going to break this problem up into two parts because we have the time where Sam is has the thrust from the jetpack, and we have the time when the jetpack turns off and then Sam starts slowing down. So we'll call like those A and B. So we're going to call this A. And we'll come back and do a new free body diagram for part B. So this will show us the first thing that we're asked is what is Sam's top speed? So Sam is going to reach his top speed when right when the jetpack runs out, so at 10 seconds. Okay, so the first thing we've got to write our givens and finds. So let's see our givens. We have that force of the thrust from the jetpack is equal to 200 newtons. We have the mass is equal to 75 kilograms. We have the kinetic friction coefficient is equal to 0.1. That is unitless. And then we have our time, delta T, when the jetpacks are still have power. That's going to equal 10 seconds. And so the first thing we're going to find A is top speed, and B is X final, we'll call it. The final, how far he has traveled. We'll call that X final. Or maybe we should call it X total. So let's call it X total. Because I think we're going to have an X final 1 and an X final 2. Okay, so we're going to start with A. And so what we want to do is take our free body diagram and turn it into, use that to create our equations for Newton's second law. So let's start with the X direction. So we're going to say the sum of the forces in the X direction. Well, we can say it's either equal to 0 or ma. And 0 would mean that Sam was moving, either not moving at all or moving at a constant speed. And we know that he's not moving at a constant speed, that he is speeding up because he has this thrust that's helping him to get along the snow. So we're going to say, okay, we know that there's a net force here. So we're going to have a net force. We'll draw that on a free body diagram. This is F net. We will have a net force. Okay, so what are our forces? Well, we see from our free body diagram, we have the force of thrust to the right, and we're going to call to the right positive. So we're going to say that way is positive x. Force of the thrust minus the force of friction is equal to ma. Okay, well, force of thrust we know. And so in order to find top speed, so we're trying to find top speed, which is v, right? So we're top speed, we're looking for v. So it'd be really nice to have our acceleration. So this is what we're looking for. So let's look for that. So we're going to divide both sides by a. So we're going to get a is equal to this side, so force of thrust minus force of friction over m. Well, we know our force of friction is equal to, so force of thrust minus mu k, so the kinetic friction because Sam is moving, and then force of the normal times the force of the normal over the mass. Well, we can use our equation in y. So if we go back and look at our free body diagram, we can see that the force, sum of the forces in y is equal to 0. And why is it equal to 0? Well, we know that Sam is not moving off the ground, right? He's not like launching into the air and he's not being squished into the ground. So we know our sum of the forces in the y direction must be balanced. So that's why the sum of the forces, the two components, are equal to 0. So that tells us we know up is positive, so force of the normal minus force of gravity is equal to 0. Solving for the force of the normal, we add force of gravity to both sides and we get force of gravity. And so we know the force of the normal, when it's equal to the force of gravity, that's just equal to mg. And we can then plug that in right here. So we're going to have A is equal to the force of thrust minus mu k times mg all over m. And so plugging in, then we have A is equal to the force of the thrust is, where do we write that? I think 200 newtons. Minus mu k is 0.1 times m is 75 kilograms times 9.8 meters per second squared, all over 75 kilograms. Okay, and so when we work out the numbers, we're going to get 1.69 meters per second squared. And now we can use that acceleration. So what's happening is if we think about, if we go back to our picture here and we were to draw a motion map, right? Sam starts out at rest, but then starts speeding up because he's got this jet, he has this jetpack, right? And so we have something that looks like that, right? So our velocity vectors here are speeding up, getting longer. So we know what they're speeding up. And so that's the acceleration that we found here. So we're going to say, okay, V final is equal to V initial plus A delta T. So we know that Sam started from 0 here. Our motion map shows us that. And it doesn't tell us that Sam starts with an initial speed. So we're going to assume he turns on the jetpacks, and the jetpacks are what shoot him across the snow. So that's going to equal to 0. So V final is equal to 1.69 meters per second squared, I got my squared here, times 10 seconds. So V final is going to equal 16.9 meters per second. So that is our answer to A. And now we're going to start B. So B is asking us, let's see, B asks us to find the x total. So in order to find x total, we need to find the distance that Sam travels while the jetpacks are on, and then while he starts slowing down because the jetpacks are off and friction causes him to slow down. So let's write B and say that we need to find x final 1 plus x final 2. And let's start with x final 1 because we already know V final. So so for x final 1, what we're going to do is we're going to say, okay, x final 1 is equal to x initial plus V initial x delta t plus 1/2 a in the x direction delta t squared. Okay, when Sam first starts, he's starting from 0. So we're going to say this is equal to 0. We know he starts with an initial velocity of 0, so this goes to 0. And so really our x final 1 from when he stopped to turns his jetpacks on until the jetpacks turn off after 10 seconds. We have x final 1 is equal to 1/2 times 1.69 meters per second squared times 10 seconds squared. And when we work that out, we get x final 1 is equal to 84.3 meters per second. So that's the distance he goes right to here. So this distance right here is going to be 84.3 meters. But then Sam starts slowing down. And this might not be exactly right, but we get the idea. Right? And so we're now looking for x final 2. And so this is our x final 2. So we need a new free body diagram because all of a sudden now this this piece of the free body diagram is gone because the jetpack only lasted for 10 seconds. Okay, so new free body diagram. We're just going to have the force of the normal. We're going to have the force of gravity. And then we have the force. So Sam is moving to the right, but the force of friction slowing him down. Okay, so we can use our same idea. We take our sum of the forces right from our free body diagram, and the x direction is equal to ma. And we know that because we can see these two are equal, but we don't have anything. This is unbalanced, right? Nothing balances our force of friction. So we know we're going to have an acceleration. So we're going to have force of friction is equal to ma. And so we're looking for a again. And so a is equal to the force of friction over m. Now we can use the same force of friction equation here, where force of friction here, right, is equal to mu k times force of the normal. And the force of the normal from over here, right, is equal to mg. And so we're going to write then the force of friction. This is our force of friction. And we're going to use that right here. So our force of friction didn't change. This is going to equal, oops, uk times mg over m. So A is equal to, cross my m's out, and I get mu k times g. So A is equal to 0. Where am I here? 0.1 times 9.8 meters per second squared. So A is going to equal 0.98 meters per second squared. And so now I want to use, so what's happening is, right now I'm on just this part. So I've got this, right, this part of the second part of Sam's motion map here. So I want to use, I think this one I'm going to say v final squared, and this is right here is going to be my v final, is equal to v initial squared. So this is going to be my v initial, minus 2a delta x. Okay, so I know the final velocity here is going to equal 0. And I'm looking to find delta x. That's, I want to know how far I'm going to go. And so really this delta x is my x final 2. So I can see here that if I bring that to the other side, I'm going to have 2a delta x is equal to v initial squared. So delta x is equal to v initial squared over 2a. I just divided both sides by 2a here to get delta x alone. And when I plug that in, I'm going to have delta x is equal to vi squared. And we figured it out over here. It was equal to 16.9. So 16.9 meters per second squared over 2 times, and our a was 0.98 meters per second squared. So our delta x then is equal to did I write that down? What is that? Let's see if I can add that really quick. Okay. So this is going to be 16.9 squared. 16.9 squared divided by 2 times 0.98. And I get 145.7 meters. And so then if I add that to 84.3, I get 230. So what I'm finding here is my x total, and I'm going to say that this is equal to x final 2. So my x total is going to equal x final 1 plus x final 2. And so that's going to equal 84.3 for the first part of his trip plus 145.7 meters for his second part. And so that x total then is equal to 230 meters.